Well, great to see everybody. Let's get started. Thanks everybody for coming. So yeah, I'm delighted to introduce today's seminar speaker, Dr. Lorenzo Rosa, he's a principal investigator at the Carnegie Institution for Science, and specifically he's in the Biosphere Sciences and Engineering division there. So I've known Dr. Rosa for more than a decade. He came as a visiting master's student when I was doing my PhD with Professor Paulo Dodorico from the University of Virginia. So we have a longstanding connection and collaboration together. Really delighted to have him here. So I'll tell you a little bit about him, and then we'll get started with the presentation. Um, so he came for his master's, and then after he did his master's at Politecnico di Milano in Italy, and then after that did his PhD at UC Berkeley and completed a postdoc at ETH Zurich. And for his work on water, energy, food nexus, climate smart ag, and circular bioeconomy systems, he's received numerous awards and recognitions. So that includes the AGU Science for Solutions Award, the Leonardo Award for Engineering, and he's also been named as a Forbes 30 under 30 recipient for science and technology. And just this past year, he was named a highly cited researcher by Clarivate as well. So beyond all of these awards, one of the things that I admire most about Dr. Rosa is how much he lifts up the people around him and enables their success. And that's really clear from the success of all of the postdocs and graduate students with whom he's worked since moving on to his position now. And another thing I really enjoy about working with Lorenzo is that he thinks really deeply about how his science connects with making food, energy, water systems more equitable, sustainable, and resilient, which I hope will come through, or I'm sure will come through in his presentation today. So in short, I think he's a really great example of not only a rock star scientist, but somebody who's really caring and empathetic and helps to uplift the scientific community at large. So we're really delighted to have him here today for his talk entitled Pathways to Low Carbon Ammonia Production for Resilient and Sustainable Agriculture. So without further ado, please join me in welcoming Dr. Lorenzo Rosa.
Thank you, Gary. Yeah, before starting, thank you very much for the invitation, and thank you, Kyle, for hosting me here. And I started my research when I was a master student, hosted by Kyle, and Kyle inspired me. So when I came to do my visiting, I say, okay, I'm just going there, do my thesis, and then I want to do the engineer, right? Classic engineer consulting. And then, working with Kyle, my master thesis, we did 2 papers. Say, I like it. I'm kind of natural, I'm good. And then I did a PhD. So I'm here also thanks to Kyle, and it's great to say this publicly. Also, many of the awards I won, including the AGU award and the water award, Kyle was the nominator. So, it's great that this department has Kyle, very good colleague and scientist. And yes, today I wanted to focus the presentation on ammonia fertilizers. Because of what is happening, if you are listening to the news, right, we see we have this conflict in Iran, right, supply chain shocks with oil, gas, but also fertilizers, right? And so this is work I started when I became PI, principal investigator at current institution 5 years ago, when a similar situation was happening. In 22, Russia invaded Ukraine, right? And price of gas went up, and also fertilizer prices went up. And so I started to focus on this topic of fertilizers. Historically, I focus a lot on water scarcity irrigation. I'm not going to focus on this today. The presentation today is mainly on ammonium fertilizers. But before starting, I grew up in the Prealpine region around Lake Como in Italy. You can see from the map, it's between Milan and the Swiss border in the Alps. And you can see my hometown, a very small town, 1,000 people in the summer and in the winter. So these are the first mountains from the Po Valley when the Alps start. As a child, I explored the landscape, and I engaged a lot in farming with my family. And I come from 3 generations of cheese and cured meat producers. So here you see the family shop with my dad and the products that my family has been making for generations. And when I was a child, in 23, well, a child, when I was younger, in 2003 and 2006, 2 heat waves and droughts hit North Italy very strongly and impacted agriculture. And so I became aware of the impacts of climate change, of these climate extremes. And so this sparked my passion and commitment to study solutions to make agriculture more sustainable, resilient. Because indeed, as I mentioned, my family, but also my region relies on agriculture, and many of the products produced there are known worldwide, like wine, Parmesan cheese, and also rice for risotto. And so this brought me to my academic journey, where I did my bachelor and master in environmental engineering, PhD at University of California, Berkeley, postdoc in energy and process engineering, and then PI at Carnegie. So I have a group, mainly of graduate students from Stanford and postdocs, and we aim to work on solutions to improve agricultural sustainability. And we are a team very interdisciplinary. We have environmental scientists, air system scientists, but also engineers, from mechanical engineering to energy and chemical engineers. This figure mainly summarizes my research. So I do system modeling for sustainable solutions. I do geospatial optimization, life cycle analysis, and techno-economic analysis, mainly focused on agriculture, but also considering multi-sectoral dynamics, considering energy systems, water systems, and climate. And so I do this research at the system level, focusing on solutions to make agriculture more sustainable and resilient, considering this multi-sectoral system modeling within the water, energy, food, climate nexus. And why I focus on agriculture? So agriculture is the most impactful human activity. 90% of water consumption is for agriculture, mainly irrigation. 15% of global greenhouse gas emissions are from agriculture. Agriculture also accounts for 5% of energy use, like on farm, 5% of energy use, half of habitable land, and also about 80% of water pollution because of nutrient runoff. So if we make agriculture more sustainable, we can solve many of our challenges about sustainability. However, we have two additional challenges. One is that climate change will strongly impact agriculture in this century, and so reduce yields. And the other impact is that in the next 30 years, food production will have to increase about 50% to keep up with demand because of population growth and changes in diets. So satisfying demand for food without causing additional environmental impacts and climate change is a central challenge of our times. And so this is why my research mainly focuses on agriculture. And today I will focus on fertilizers, which are very important, ammonia-based fertilizers, which are very important inputs for agriculture. So this figure shows the emissions from agriculture and how to reduce the emissions in agriculture. The bar graph shows that the emissions by sector in agriculture only, which, as I mentioned, are 15% of global greenhouse gas emissions, about 7 gigaton. And the emissions are mainly coming from energy use on farm, which is machinery and irrigation pumping, fertilizer application and production, methane emission from rice cultivation, we have livestock with enteric fermentation, and then we have residues from crops and manure that usually are left on the ground to decompose, and also these emit emissions. And in 23, we published a study that basically lay out a pathway on how to achieve net zero emission in agriculture. We study different strategies and their theoretical potential to achieve net zero emissions. And so some strategies are to decarbonize energy use on farm. Another strategy is to sustainably manage nitrogen and fertilizers. One is alternative rice cultivation methods to reduce emissions from rice, then to have better feeding and breeding, so to improve the productivity and efficiency in terms of how we produce livestock. We have also technologies to use agricultural waste and residues like manure and crop with a circular bioeconomy approach to produce bioenergy and carbon capture. This was mainly the focus of my postdoc. And then to achieve net zero emission, we need negative emission with agriculture alone. Even if we would use all these strategies, which obviously are very expensive, and this is the theoretical potential, is not enough. So we will need negative emissions, so remove emissions, CO2 from atmosphere and store it somewhere, or underground or in products material. We need strategies like enhanced rock weathering, where you can spread rocks and do carbon capture on farms. And most of my research focus on three of these strategies: decarbonization of farm energy use, nitrogen management, and bioenergy with carbon capture and storage. And today I will mainly focus on the nitrogen and ammonia fertilizers topic. So why I'm focusing on this? Again, because of what has been happening in the past few weeks. So this figure shows the price of fertilizers, the green line, in the past 24 years. And we see that we had a spike in prices when Russia invaded Ukraine, right? And also in the past 8 weeks. And according to the World Bank, every 1% increase in fertilizer price translates in about 0.45% increase in food commodity prices. So when price of fertilizers go up, food prices go up, and so food security issues, especially in the global south. And this work that I'm going to present is also prominently featured in many news outlets. When the war started, basically every other day, a news outlet contacted me to ask me questions. For example, the World Economic Forum highlighted this work in this article, another conflict, another reminder of the fragility of the world food supply. And through this presentation, I will show the supply chain, the production, and how to solve it, how to make more resilient this production and these systems we have today, showing a lot of maths, a lot of geospatial analysis, because at the end is an issue between supply and demand. So transportation is a big issue in this way we have today when we produce fertilizers. And so the question that we try to answer is, how can we engineer low carbon ammonia fertilizer systems that are scalable, resilient, and compatible with energy and agricultural systems. So today, fertilizer, as I mentioned, are produced with ammonia. Ammonia is a chemical that is produced with the Haber-Bosch process. The Haber-Bosch process is a 100-year-old process. 2 Nobel Prizes were won thanks to this process. And it's very energy and carbon intensive. So today we use natural gas and coal, where these energy conversion processes, steam methane reforming and gasification, to produce hydrogen. Hydrogen is very energy and carbon intensive. We purify the hydrogen, and then we combine nitrogen from the air, from air separation, with hydrogen at very high pressure and temperature in very large facilities today, in chemical refineries. And with the Haber-Bosch process, we combine hydrogen and nitrogen to produce ammonia. So this is a very simplified way on how we produce this very important chemical today. This process uses 2% of energy, 3 to 5% of natural gas, which is mainly fossil natural gas. About 1/3 of hydrogen is used to produce ammonia. The other 40% of hydrogen is used for refining of crude oil, to purify the crude oil. As I mentioned, hydrogen is the main issue. 90% of energy use and emissions are from hydrogen production, very energy intensive. This process emits 450 million tons of CO2 equivalent. As you remember from the slide that I showed, ammonia fertilizers emit 1 billion ton, so 1,000 million ton of CO2 equivalent. So the production emits 450 million ton. The other 600 million ton are from the application. So the way we apply fertilizers is very inefficient, and so we emit nitrous oxide. The focus of the presentation today is mainly on production, so on these emissions. But if we want to really cut emissions from fertilizer, we should also manage the application with more efficiency, precision agriculture. Very importantly, this process feeds half of the global population, 3.9 billion people. So 1/2 people are fed because of synthetic nitrogen fertilizers. And we quantify, for example, how many people are fed from food grown with synthetic nitrogen fertilizers in each country. For example, in India, more than 600 million people are fed from food grown in India with synthetic nitrogen fertilizers. We check US more than 400 million people because US is a big exporter, right? So the US grows food for more than 400 million people with synthetic nitrogen fertilizers. So these reliance on large facilities, fossil fuels, and the importance on ammonia to produce fertilizers and then produce food, expose food systems to energy and supply shocks, as we've been seeing in the past 2 months. As I mentioned, about 70% of ammonia is used today as a fertilizer. The rest of ammonia is for explosive, plastics, and textile. We use mainly natural gas, coal in some countries like China, South Africa, and very little low carbon, like electricity. We have ammonia, but ammonia today is mainly applied as a fertilizer. So we have different fertilizers. One of the main fertilizers is urea, which is solid. We have also nitrates and other fertilizer compounds. So once we produce ammonia, there is another step that is to produce the fertilizer, which depends also on the farming type, on the technology that the farmers apply. And it is also very important. So farmers today don't apply ammonia directly because it stops. Excluding some exceptions, for example, here in the US, because we have big machineries and some farmers, for example, in Iowa, they are able to apply directly ammonia in the soil with these big machineries. But very important, today ammonia is mainly applied as a fertilizer as a fertilizer in agriculture. So these maps show the production and the demand of ammonia fertilizers. The red dots, the map in the top shows the 406 facilities where we have ammonia production. So these large chemical refineries where we have the Haber-Bosch production at high pressure and temperature. And these facilities produce millions of tons of ammonia per year. So they are very big, like big chemical refineries. And they are mainly located in some countries and regions. And for example, you see that in Central South America, in Sub-Saharan Africa, but also in Southeast Asia, we have very few facilities. And you can also see that there is a mismatch between where we produce the fertilizers and where there is 70% of demand of ammonia, which is where we have agriculture. So in blue, we have regions where we have agricultural that is intensified, high demand. In yellow, where it's not intensified or it's not yet intensified, but there is demand or there is potential additional demand. And so this supply chain mismatch between production, the red dots, and demand in agriculture creates a complex supply chain with transportation, imports, exports, that expose indeed the food production for half of the global population to these complex supply chains. And in fact, about half of fertilizers today are traded globally, creating very complex logistics. And very interestingly, 40% of exports are controlled only by 4 countries: Russia, China, Qatar, and Saudi Arabia. So this figure shows the main exporters by value in dollars: China, Russia, Oman, Qatar, and the main receiving country. For example, a big flax is going from China to India in terms of fertilizers. This is in terms of dollar value. And so this shows the complexity of the supply chain, and that a very few countries control the main exports of these very important input in agriculture. And indeed, when Russia invaded Ukraine in 2022, we started to work on this, and we quantify the vulnerability to supply shocks. So these 2 maps show in green countries that are net exporters of fertilizers. So in the top figure, we see in green net exporters. So for example, Germany has a big chemical industry and produce enough fertilizers from ammonia to meet the domestic demand, but also as a surplus for export. Okay. While in orange and in red, we see net importers of fertilizers. The figure in the bottom, we show the same, net importers and exporters, also accounting for natural gas, because as I mentioned, a lot of this ammonia is produced with imports with fossil fuels like natural gas, and many countries like Germany they rely on imports of natural gas. So if we account for imports of natural gas, many countries that are in net exporters of fertilizers, they turn in on net importers because they rely on fossil fuels, in this case natural gas, to produce these fertilizers. And so countries like Germany becomes net importers. Okay, and as you can see, very few countries are in green, so they are net importers of fertilizers, and they also own the fossil fuels to produce these fertilizers. And basically because they have the chemical industry to produce the fertilizers, but they also have the natural resources, in this case natural gas, to be self-sufficient, energy secure in terms of production. And these countries are mainly the US, Canada, Gulf countries, and Russia. And what we also quantify based on diets and balance sheets, the number of people that are fed from imports. So as I mentioned, half of the population, 3.9 billion people, is fed from food grown from fertilizers. If we account from imports of fertilizers only, we found that about 1.4 billion people rely on imports of fertilizers. If we add the imports of natural gas, this number grows to 1.9 billion people. So this to show that about 1.9 billion people relies on imports of fertilizers or fossil fuels to produce the fertilizer, and to show the importance of this mismatch in the supply chain, supply and demand that we have today, and the fragility and vulnerability that we have to supply shocks in agriculture. So what we did was to study different routes, different ways to produce low carbon ammonia. So this was more chemical engineering, process engineering work. So as I mentioned today, we produce ammonia with coal and gas. We do gasification or steam reforming. We produce hydrogen. Then we combine it with nitrogen at high pressure and temperature with the other Bosch to produce ammonia. Well, ways to produce low carbon ammonia. Some are centralized, so still larger scale. They can be larger scale. And simply, instead of using coal, gas, we can use local biomass. So with a circular bioeconomy approach. So this would use not local natural resources. Obviously, biomass is not unlimited, right? It's a finite resource, but we could offset a fraction of fossil fuels and use biomass to produce ammonia. We can also do carbon capture to reduce emissions, point source carbon capture. The other way to produce low carbon ammonia is with electrification, so using grid electricity, solar, wind. And this technology, the electrification that produces hydrogen with water electrolysis, but also the natural gas one and the biomass, very importantly, now we have new technologies that allow this to produce it more at small scale, lower pressure, temperature. So this allows you to go from a centralized large scale facilities with millions of tons of production per year to thousands of tons of production per year, because you don't need the high pressure, high temperature, and economies of scale that we need today. And this is called Haber-Bosch 2.0. So it's a new technology readiness level 7, 8, so almost commercial, that allows you to produce at smaller scale production, so close to the farm, county level or farm level if it's a large farm, okay? And so what we have been doing is to study how we can restructure the ammonia industry, going from the centralized way we have today, 400 facilities, trade, large scale production, 2,000 to 3,000 tons of ammonia per day, so huge facilities. These are literally chemical refineries with trade and fossil fuels, to more decentralized production, so local scale production. For example, these are rendering of a facility, very smaller facility, right? Yeah. About 100 tons per day, even 20 tons per day, so very small scale, without trade, local production or limited transport, and using low carbon electricity or local biomass resources. And what we study are what are the advantages of decentralized ammonia production compared to centralized production, and the associated environmental and techno-economic implications. And I will show the results, mainly focusing on the US, of the techno-economic and life cycle analysis we did of the large-scale production and the decarbonization pathways with small-scale production. So the US has about 33 production facilities today, the red dots, which are about 9% of global production capacity. The US is also a big user of fertilizers after China and India. The demand is in the blue and yellow counties based on agricultural demand. And very importantly, the US is not self-sufficient. So the US produces about 80% of its fertilizers. The other 20% is imported. And so there is still a dependency, even for the United States, in terms of imports of some of these fertilizers. And so what we did, this is a short explanation of the methods. We quantify the cost of producing centralized ammonia, and we compare it with the cost of producing decentralized ammonia, assuming that decentralized ammonia can be produced locally without the transportation cost, while decentralized ammonia needs transportation cost. And so another explanation of the methodology. So we have ammonia production and demand in the United States. We first quantify the transportation cost with a linear optimization model that minimizes cost, and matching supply and demand, and considering also the availability and the demand, and we quantify the transportation cost for decentralized production. Then, considering historical prices of fossil fuels, coal and gas, we quantify the cost at each production facility today. And then, summing the cost of transportation with production, we can quantify the cost of centralized ammonia production at the farm level today. Okay? And then we compare it with the cost of decentralized production, considering grid electricity and renewables from solar and wind. And we assess the so-called levelized cost of ammonia, which depend on capital expenses and operational expenses, CapEx and OpEx, and also the discount rate on the loan. And then, assuming that it's produced locally, we quantify the cost of producing ammonia with local availability of natural resources, in this case, solar, wind, or grid electricity. And this figure shows the cost of producing ammonia for each of the 33 facilities in the US. This is using the price of fertilizer in 23. And as you can see, the cost is between $200 and $300 per ton of ammonia. This is large-scale production. Then, as I mentioned, we transport this ammonia, so we quantify the transportation cost. And this map shows the transportation cost in each county in the United States. And as you can see, there are some regions, the regions in yellow, where the price is almost $80 per ton, because indeed of transportation distance. This is just considering transportation distance. We didn't account for additional cost markup because of exchanges between ownership or additional fees. But the transportation cost makes the price go from $300, $400 to and about additional up to $100. And Midwest, where there is big demand, also West US, big cost, because there is no local production, there is transportation. And these summarize the geospatial results here, this paragraph, by state. And for example, California has a price that range from $30 to $180 because of the geospatial, the transportation cost that exists in the state, and similar for other states. So on average, the median transportation cost is about $40 per ton in the US. And then we quantify the cost of centralized production, right? So summing up the cost of production at the 33 facility plus the transportation cost, which is the first line, with optimistic reference and pessimistic fossil fuel prices, right? In over 20 years, the cost of fossil fuels change. This is, we use just one bar color. As I mentioned, the cost here is between 300 and 600, right? But it's just blue, because the cost of decentralized ammonia with solar wind is way higher, can be up to $1,000. And in fact, the two other lines show the cost of decentralized ammonia with grid electricity and renewables, considering an optimistic case with cheap grid and electricity, a reference case, medium value, and pessimistic, lower cost. But these basically summarize the cost. So the cost of producing ammonia today plus transportation, the median cost is about $300 with natural gas, 500 with coal. There are also two facilities that use coal in the US. And then decentralized is about 1,000 to 1,500, right? Because indeed fossil fuel prices are very cheap in normal times. And indeed, this figure summarizes the results from the geospatial to the state level. And as you can see, in green is the cost from 2000 to 2023 of producing ammonia with fossil fuel-based centralized production. And there is a range because in the 20 years, 20 years plus 12 times 12 months variation in the fossil fuel price. In orange is the grid base with electricity, decentralized, and in purple with solar. And the solar cost is higher because the sun does not always shine, and so you need some battery storage, and battery storage is very expensive now, and so increase the price of the production. And very importantly, the price of ammonia, this was April 3rd, now is very high, is about $1,000 in the Midwest. So this technology for a few months or a few weeks like now is cost effective. Obviously the issue also in the past and also that for a few instances was cost effective is for how long, right? But during periods like now with very high prices is cost effective. And the question is for farmers or like users, do I want energy security for long term? And so I'm willing to pay this additional green premium, or when the crisis, the supply shock happen, I just lose production and potentially disrupt all the facilities and supply chain and farming activities. So what we did was also to study the tax credits, how policies basically can help to make these decarbonization policies of ammonia cost effective. And so we studied the Inflation Reduction Act from the previous administration, which gave two tax credits. One is the 35V and one is the 45Q. So 45V basically was giving $3 per kilo of hydrogen with a very low carbon intensity of about 0.45 kilo of CO2 equivalent per kilo of hydrogen. As I mentioned at the beginning, ammonia is very carbon intensive because of hydrogen, right? 90% of the emissions are from hydrogen. So if you were producing low carbon hydrogen, you could produce low carbon ammonia, and so you could get the tax credit. This is the 45V. And then we modeled also the 45Q, which was with carbon capture and storage. So you capture the CO2 emitted during production of ammonia, and then you store it in geological formation or in materials, and you could get $85 per ton of CO2 sequester from these industrial activities. That can be ammonia, but many other facilities. And so we show here the results. In blue is the cost of ammonia without decarbonization policies. Business as usual is today, right? Now, as I mentioned, is between about $300 with ranges based on the facility, especially the coal facilities in the US are more expensive. And then we show with carbon capture, biomass with carbon capture, and electrification using wind and solar, the cost. And as you can see in blue, the cost of low carbon is higher, right? With CCS, the most cost effective after business as usual. If you account for the two tax credits, 45V that is orange and 45Q that is green, you see that they become more cost effective. And some strategies like wind and biomass with CCS, even carbon capture and storage are more cost effective than business as usual. Obviously, this if the two policies were in place, they were taken out last year. But in 24, before the election, many ammonia producers, they were actually considering and started to build some of these facilities. I don't want to go in detail, but basically they can still claim the tax credit if they finish construction by 28. This takes a lot of time, but some of these basically oil and gas majors that are producing ammonia are aiming to still claim the production, meaning with CCS, blue ammonia is called, especially in Texas and Louisiana. And so if they are able to meet these requirements to finish by 28, they can produce ammonia very cost effectively, claiming the tax credits. So this to show how policies, they can help to reduce the green premium, even with low fossil fuel prices, and so they can make this technology more cost effective. Another way to produce ammonia on top of electricity is biomass. As I mentioned, this more circular bioeconomy approach. We have a lot of waste biomass. And I call this biomass sustainable biomass because it's coming from manure and crop residue. So it's waste biomass from agriculture, which today is emitting emission when decomposed on the ground. We can reuse this biomass by collecting it to produce biomethane or natural gas using anaerobic digestion. This is a very widespread process technology. And then simply we switch from fossil natural gas to renewable natural gas, and we produce ammonia as we produce it today. And this technology basically is very seamless. You just have to do a fuel switch, right? It's like in your car, instead of putting fossil gasoline, you put renewable gasoline, right? So you don't have to change your engine. And you reduce emission with this. And so this technology can reduce emissions a lot, going from 1.8 tons of CO2 equivalent per ton of ammonia to 0.19 if you would fully substitute biomass. So this figure shows biomass substitution rates from 0 to 100%, and how the emissions of carbon intensity of ammonia decrease the more we use renewable natural gas. And if we use carbon capture and storage, with just 10% biomass substitution rate, we can achieve net zero emissions. If you use more and you continue with carbon capture and storage, you can even do negative emission. So this to show how biomass can help to reduce emissions. And so what we did was to quantify the availability of waste biomass, which is in blue. And in geospatial analysis, we know agriculture, how much crop residues we have, so the straw from corn, from soybean, for example, how much we can sustainably use, take for anaerobic digestion, the same for manure. So we have manure, how much is left on the ground, how much we can use, and then how much renewable natural gas can be produced. The blue areas is where you can produce a lot of this. And then with geospatial analysis, we quantify the availability of this biomethane within the 33 facilities, the red dots in the US. And so we quantify if there is enough availability to meet demand and the distance. And so summarizing some of the results, so we identify high impact facilities where there is enough biomass. And for example, we found that facilities that are in regions with a lot of biomass and very low demand of biomethane, obviously they can fully use and decarbonize the facility with the biomass, while facilities like this one, but there is a cluster of facility, not enough biomass, there is not enough local biomass, right? So we will need very long transportation to bring in the biomass. And in fact, some of the facilities we need to transport more than 100 miles, so very long, unfeasible, right? This biomass to meet the demand. But in theory, if we would use all this sustainable waste biomass, we could decarbonize about 75% of ammonia production in the US. Obviously, biomass is limited, right? Long transportation, but biomass can cut some of the emission or can be reused with this circular economy approach to decarbonize and produce ammonia with local energy resources instead of importing natural gas. What I want to show is also like more the global picture now. So this is a study we have in review. And basically, we quantify the transportation cost globally. Again, with an optimization model that minimize cost, matching production with demand, supply and demand. And so what we found is that, the US I've shown before, right? The cost is up to $100. But if you consider the global south, where you have very few facilities in some regions like Central America, South America, Sub-Saharan Africa, Southeast Asia, the cost is way higher. And in fact, here in yellow, you see the countries where there is a super high cost because of the transportation. This is just transport alone of ammonia and can reach up to $300, $350. So double of the cost just with transportation. Then you have all the markups among all the intermediaries, right? And so the average transportation cost global is about $80. And the cost in some regions like Brazil, Uruguay, Chile, Democratic Republic of Congo, Nigeria, is up to $300. And so here are at least the countries with the higher cost, like Paraguay, and then we have Congo, Nigeria, Mozambique. So just to show how the farmers in these countries they basically pay double of the cost of the fertilizer compared to other farmers, for example, in the Midwest, that they are closer to the production of ammonia and fertilizer. And so this map then shows by country the impact of transportation cost on the total cost of fertilizers. And so in dark blue, you see, for example, in Brazil or in some African countries, more than 50% of the cost of the fertilizer is because of transportation. And without accounting indeed for the differences in fossil fuels. So as you can see, even Mexico, right, they really high price. Many countries in Sub-Saharan Africa, South America, and some also in Southeast Asia, because they don't have domestic production, because it's very far away. They pay a very high cost. This is just transportation. Then there are all the additional markups, right? And in some countries, the price, I was checking Uganda, it is a landlocked country, the price is almost $2,000. This is because it is transported, let's say, from the US or China, reach ports here, and then it has to be transported inland. So, very cost ineffective, right, for farmers, and basically that's why they don't apply fertilizers in some locations in the global south. And so this is why technologies like decentralized, they could basically reduce this cost gap, right? Especially in these countries where there is a super high transportation cost, excluding the price shocks with fertilizers. So far I've shown the techno-economic work, so to show the cost effectiveness. I want to show also the environmental impact, so the life cycle assessment work. And very importantly, most of these technology are more energy, land, water intensive than business as usual. And the main explanation for this is because we need hydrogen, right? And hydrogen is contained in the chemical compound of natural gas and coal. While when we use electrification, we need to produce the hydrogen molecule from electricity. So these technologies are very energy, water, land, and natural resource intensive. These are logarithmic scale. So off scale would be electrification, that is very energy intensive compared to, for example, carbon capture and storage and biomass. Biomass obviously use a lot of water because we need water and land to grow biomass. But this is just to show now we need a lot of natural resources to produce these chemicals. They can be ammonia, but any other chemical, methanol, plastics, because the fossil fuels contain the hydrogen molecule, and to decarbonize these products, we still need hydrogen, and hydrogen production is very energy, and so also water, land, and natural resource intensive. And so we highlighted this in this paper, net zero emission chemical industry in a world of limited natural resources. Very impactful study, where basically we show, okay, we can achieve net zero in the chemical industry, which is ammonia, plastics, and methanol, but many countries will be limited by natural resources. Here we show land scarcity, water scarcity. This is done at country level. As you know, water is a local issue, right? So countries like the US, you go from very wet to very dry areas. But just to show, aggregating the results, many of the countries, so basically half of the countries will not have enough land and water to locally meet demand for a net zero chemical industry without exacerbating land scarcity or water scarcity, so without cutting down additional forest or without depleting environmental flows. And we've done this with carbon capture and storage, electrification, and biomass. So some countries will be constrained from sustainability point of view in terms of land and water to actually domestically produce the chemicals to achieve net zero emissions, without compromising natural resources like forest with deforestation or water resources with water scarcity and environmental flows. And I just want to show very briefly this study. So as I mentioned, part of my work is also about water use, water scarcity. And so we did a study recently on the direct and indirect water use from ammonia production with life cycle assessments. And in green, you see the direct where there is the facility, direct water use from life cycle assessment with ammonia from steam methane reforming from natural gas and coal gasification. This additional water use is indirect water use, so it's from the full life cycle assessment, so it's water used along the supply chain to produce the fuel, to produce the facility, to produce the components that go in the facility. And so it's very important to show direct water use, but if you account also for indirect, the water footprint is more than double. Obviously, this water is used in most cases somewhere else in a very different location. But what we did was to quantify with the work I've been doing with water scarcity for each of the 400 ammonia production facilities in the world, the exposure to scarcity. Here shown in terms of number of months with water scarcity from 0 to 12. 12 is dark. Basically, when you have water scarcity, it doesn't mean you don't have water. It means that you are using water in an unsustainable way, depleting environmental flows or conflicting water with local user, that can be irrigation or domestic sector. And we found that about 18% of production is facing water scarcity, at least 1 month per year. And so factoring water availability into plant siting, into facility siting for future facilities is important for resilience and sustainability to avoid potential water competition and water issues. And in general, also other natural resources. Here I'm showing water, but can be biomass, can be land, many other natural resources. And here again to show like the supply chain, for example, China is exporting ammonia fertilizers that feed 269 million people, of which 18% is in water scarcity. And the production is mainly going to Brazil, India, and Malaysia. Russia exports ammonia that feeds 196 million people. No facility are in water scarcity. And the main fluxes are going other countries and Brazil and United States. So this to show how water scarcity at the production point then spreads to other countries with the imports, exports, in the concept that is known as virtual water. So you virtually export the environmental impact to another country. So the importers of ammonia fertilizers, they also import the risk of water scarcity or any other risk that you want to consider from where the fertilizer or any other commodity is produced. So I wanted to show here this telecoupling between the impacts in a location, how they affect, or they could potentially affect the user in another location. And to conclude, so this research, I like this research because I've done good research, good publications, but I was also able to translate this research with industry collaborations and technology transfers. So I'm an advisor of a startup called Ammobia, it's a San Francisco-based startup that is developing Haber-Bosch 2.0. So they are building the Haber-Bosch process that I suggested at a small scale, lower pressure, lower temperature. That aims to produce at most about 100 tons per day, not 2,000, 3,000 tons per day. So this can be more small, modular, and soon announcements will come out about a pilot facility with about 10 kilo per day, demonstration pilot facility, but also a large scale demonstration facilities in progress for about 10 tons per day. So the technology, to show that the technology is ready and we're reaching technology readiness level 9, which is commercial production. And so with this collaboration, what I do mainly is to incorporate the advances that they are doing at Ammobia at the molecular level into my analysis at the process system level. So we create this loop, right, where I incorporate their progresses, I generate the results, and then they can see the results, and basically they can improve or focus on specific points. So I really like this interaction. I'm often also like working directly with industry. Next week I'm going to Houston to an industry conference to speak about this, to make exactly this presentation, so to show the issue and how we could solve the issue. And also this work has been used in policy reports and agricultural extension, especially here in the Midwest, in Minnesota, where there is big need for fertilizers. They pay a lot for fertilizers, and they have a lot of curtail wind that they can use to produce locally ammonia. And so in conclusion, I've shown how the reliance today on large-scale facilities creates supply chain shocks, trade dependency, and this cost build-up, right? Technologies like electrolysis with solar and wind or grid electricity and biomass eliminates the use of fossil fuels, and basically they reduce this reliance on natural gas imports. I've also shown that low carbon and decentralized production can produce locally ammonia without relying on transport, improve resilience, sustainability, and also very importantly, can create local jobs, okay? Because if you have a local facility, you need local workers to run the facility. But there is a green premium most of the time, is more expensive, and it has environmental trade-offs that we need to consider when we design every new technology that can be from AI to decentralized ammonia. We need to consider these environmental trade-offs to have a long-term sustainability. And so that is also equitable for the local populations where we have these facilities. And so there are strategies like the Inflation Reduction Act and, these tax credits that can make it more cost effective. And also like, technology transfer, carbon pricing can make it cost effective even in times where there are low fossil fuel prices. So in this presentation, I like it a lot because it shows in a very holistic way the work I do system level, process level, collaboration and industry transfer, considering techno-economic analysis, life cycle analysis, policy, and geospatial optimization. And lastly, I want to conclude also thanking the funders that I had, really private donors and private nonprofit foundations that supported this work and made it happen. So thanks to this funding, a little bit here, a little bit there, I was able to continue this research for almost 5 years now, and so do like very deep work in this direction. And with this is the end of my presentation. Thank you so much. This just to show you is a tractor spreading fertilizers, and I thank you very much for your attention. Thank you. Yeah.
Any questions, folks? Feel free to raise your hand.
I make two questions. I was wondering, in the case of the US, you know how is the market structure? Are there few producers or is competitive market? And the second question was that you calculate how this cost can be affected if you have this Inflation Reduction Act, right? So I was wondering whether you have calculated how much would be, if it's possible. I know this is very difficult these days, but how effective will it is you can make this cost if you introduce some carbon tax?
Yeah, thank you for the question. So to answer the first question, very few producers. There are only 400 facilities worldwide, right? Mostly owned by few companies, mainly chemicals and large companies. I think you can count them on my hands in the US, on my fingers in the US. And also, along the supply chain, very few companies are handling the fertilizers. And so let's say this decentralized approach, this is why I'm going to this conference next week. I want to see if they feel threatened or if they are embracing this technology, right? But yes, very few companies controlling, like oil and gas companies are very few, right? Second question on the Inflation Reduction Act. So there were these two policies, no? One on hydrogen. If you produce low carbon hydrogen, you get the credit, and so you produce lower cost ammonia. And the other one is the tax credit on carbon capture and storage. There are also carbon credits. These are in place in Canada. In the same study we did the simulation, and yes, they make it cost effective as well. So in that study, I didn't show it here. We analyze US and Canada. In Canada, there's also few facilities. In Canada, they have the CCS tax credit, but also the carbon credits for emissions. and basically they reduce the cost. But you know, as we know, as we've seen, you need someone to put them in place, right? And you know, the big thing with CCS is that it's a very logistical, complex framework, right? You need to capture, and it's a complex technology. You have to transport the CO2, and you have to store it and monitor the storing. So it's a complex endeavor, right? And but you know, technically it's feasible, but you know, is also part of the engineers, like, you know, the companies to make it happen with help from policy, right, to make it cost effective. Yeah, thank you.
So in one of your maps, I believe you showed the US and the demand for ammonia fertilizer. And it seemed to me, if I remember correctly, that in the Midwest, there was no demand at all. And it was concentrated on the East Coast.
This one?
Yeah, something like this,
Yeah.
with the gray. And so it made me wonder what crops actually need ammonia as opposed to something else for fertilizer.
Yes, nitrogen fertilizer, ammonia.
Yeah, yeah.
So here we grow also a lot of soybean. That doesn't need a lot
So
of
soy.
yeah. Like, you know, corn needs a lot of right. And here there are no croplands. There is mainly livestock systems.
So
Which
there's
you-
no agriculture, basically. or
Well, this
very-
country level, county level, right? Obviously, maybe there is a very small demand, but in the USDA data, they don't, like, you know, it's so small that they don't show it because here is 2,000 tons per year per county, the lowest value. And so here is mainly livestock systems, you know, when you fly over, you see.
So you're saying that basically any crop needs nitrogen fertilizers.
In theory, yes.
So we can't get away from this.
Well, is the pillar of our proteins and also crops.
No, I
Like, you know, there are like these legumes that in theory they do nitrogen fixation, which is another way to produce the fertilizers. People are studying this, maybe from the biology point of view, even to make rice do the nitrogen fixation.
Mhm.
Now only legumes, soybean. So this is also why production is very low, right? The demand is kind of low because they do corn and soybean, and they alternate, and so you need less.
Yes.
And you know, fertilizer is actually half of the cost to run a farm operation. So it's big. And this is in normal times, just think now. So it's fuel for the tractor, for drying the grain, right? And then the other big cost is the fertilizer. So while corn is about 10 tons per hectare, soybean is 4 tons per hectare, right? So obviously corn is better to give it as feed for animals. They need also this trade-off between corn and soybean. So the US is doing this corn soybean system, Brazil as well, very big, right? South America, because of this advantage, the regeneration of the soil.
You click on the chat real quick. Yes. I read your question there through the.
Many thanks. No, thank you. Yeah, not chat.
What about questions? Oh, yeah, plenty of hands. Javier, why don't you go and we'll have Kelsey, then we'll have Lana. Yes.
Thank you for the great presentation. It was very informative for myself. I was wondering in your case studies analysis, if you have looked at the cost benefits of small plants for biogas production, especially in the US, the feasibility, and what's the best source and the cheapest one maybe we can produce biogas. I know one of the sources can be wastewater treatment plants from sewage and waste. So what other options we have?
Yeah, as I call it, sustainable biomass or third generation biofuels, which is crop residues, so straw from corn, soybean, you know, basically not the not food part in the crop, livestock manure. Another source of for biogas in anaerobic digestion is organic municipal solid waste. And then you have all the wastewaters, right? So these are, as we call it, more wet biomass, that you can use it as a feedstock for anaerobic digestion and then produce biogas. And biogas is half CO2 and half methane. Another way is forestry residues, but this is more dry biomass. And in theory, it's better to do gasification to produce the biogas. So it's a different technology. But you know, there is huge potential, and this is what I've shown in here, right? In blue is where we have crop residues manure and how much biomethane you can produce from biogas or anaerobic digestion of the feedstock. And this is part of my work as well, mainly postdoc and some work we've been doing now. Also, this topic is gaining a lot of traction, so circular bioeconomy, also in the US, in the Midwest a lot, Europe huge, because they import natural gas and they are finding every possible way to reduce the imports and, reusing what we waste and make it into energy is a big topic. So there is big interest here. And so this is a circular economy approach. Instead of being linear, right? We use it, we waste it, we recycle the energy and the nutrients. This has also a lot of nutrients, right? So you can cut the use of fertilizers. And we've done some work, I'm not presenting here today because of time, but we have some work that you can recycle mainly nutrients from manure. Manure has a lot of nitrogen. And so you can cut a lot of synthetic fertilizer use, but there is again a geospatial mismatch between livestock systems and crop systems. So you need to transport the manure, and manure is very wet, very difficult to transport. You don't transport it more than 1 mile. And so is another big issue. Or the solution would be to as we were doing in the past, right? Livestock system and crop system co-located in the farm. But we are not doing this for efficiencies, right? A large scale production and efficiency. Yeah. Thank you. Yeah.
Have a question?
Let's prioritizing the grad students along. Sure, okay, great talk. I'm not that familiar with some of the science, but I've sort of heard that there's a lot of concerns about carcinogens and ammonia production plants, and I was wondering, like, does that become more of a concern and create more plants and like decentralize them, or are like carbon capture technologies and things like that decreasing concerns about?
Yeah, good point. So first, carbon capture is for CO2 capture, so it's another thing. So we capture CO2 to avoid greenhouse gas emissions, right? And facilities like ammonia is very easy to capture because we have, so basically the issue with carbon capture, which was my focus in the postdoc, in a separation processes lab, so chemical engineering, basically the more diluted, the more difficult it is to separate, right? Similarly, when you do desalination, when you have very salty water, you need more energy to make pure water. And so when you have a pure stream of CO2, it's very easy than a stream with pure nitrogen, right? And so in ammonia production, actually, you have a very pure stream of CO2, about 50% CO2, 50% nitrogen, so it's easy to separate. And compared to, for example, for direct air capture, so capturing from the atmosphere or natural gas. So you need less energy and is more cost effective. And so this to answer the CCS one. You raise a very important point, which I didn't touch, but is very important. So ammonia is a toxic, explosives, right? And obviously is a chemical refinery. You have accidents, right? Is basically it's just matter to have regulation and make the company comply with the regulation, right? The ammonia, basically, this is also why we don't apply directly ammonia, because you need very technical know-how. And we just do it in a few states here in the US, mainly in Iowa. So they have these big tractors and they inject it in the soil. But on average, 1 farmer dies per year in handling ammonia in Iowa. So just to show, obviously, it's not a game, right? And another thing, when we transport ammonia, we tend to transport ammonia with boat or truck. Train company don't want it because it's very dangerous. Or if they have an ammonia truck on the train, they have to first deliver ammonia if it's too far away, and then they have to deliver the others. This is because of insurance issues. And so yes, it's a very important chemical, but we have to handle it properly. Also, the other concern is for decentralized to make explosives, right? So security issues. But you need also the know-how to make this kind of stuff. And but yes, you can have also ammonia venting in the facility, and it just matter to know to have proper engineering control and safety in the application. Yeah.
That would be helpful.
want to ask you a question.
Yeah, sure. Yeah, great, thank you so much. Not my field, so hopefully it's not ignorant question.
No worries.
So this is great thing of the slide up. So I was gonna ask about the biomass production kind of methodology for the decentralized plan approach. What is the seasonality of this? I assume nitrogen can be produced year-round, but the biomass can only be produced during like a harvest season, right?
Yeah, so this is a very good point. So in the US, but also in many other countries, we apply fertilizers mainly 2 times per year, November now. And so this is also why there is big concern with what happening in February, March and now, right? Because this is the planting season, we need the fertilizer. So the 2 big applications are with the big, large centralized system, you have a big shipment coming in, you apply it in November, and then you apply another time in the spring as a farm. Obviously, ammonia production, as I mentioned today, the 400 big facilities or 33 in the US, large scale, high pressure, high temperature, you cannot ramp it up and down. So it's like a nuclear power plant. Nuclear power plant runs for years, and then when you shut it down, you do maintenance, and then you take months to ramp it up again. And as well, these are, basically the pressure vessel has a thickness like this, because this is a very high pressure and temperature, right? And so it's very difficult to ramp up and down. The other Bosch 2.0 is lower pressure temperature and can be ramped up and down easier. So it's more flexible, as we call it, so can follow the renewables. So you need less battery storage, lower battery storage. Okay, so this is what we are working on with Ammonia, the startup, for example. This is more energy system stuff, okay? The biomass question, right? Because I answered 2 questions, I missed the biomass. So biomass, obviously, you have the harvest season, right? Manure is daily, right? But we didn't account for this annual biomethane potential per year. But yes, it's a good point. So you will need to have storage, right? And, to do a management of, okay, we have this amount of manure coming in every day, the amount of biomass mainly coming in at the harvest season, and right, you have, this is another step, in the engineering part, in the design of the system. But yes,
do you think that approach is more vulnerable to like climate risks, like you have a bad?
Yes, if you have lower yields, you have lower also waste biomass, right? In my opinion, the biggest issue with biomass is transportation again, because this is wet biomass. You don't transport it more than few miles, like literally very few miles. And 100 miles is crazy. No one is going to transport, because you're literally transporting water, right? It's very wet, and so it's a big issue. But yes, this is more like temporary grain resolution. Obviously, they affect the process, and obviously climate change has the impact. Climate change can impact food production, so lower corn yield. You have also lower straw, right? That is the waste. But I wanted to show this just to show that we have this unused biomass that can become, with circular approaches, circular bioeconomy approaches, a resource. And not only for ammonia, can be used for many other stuff. Can be used for heating, electricity, right? You can do cogeneration. You can inject it in the gas grid only when you produce it. You can use it as transportation fuel. You can use it in many things, offsetting fossil natural gas with renewable natural gas. If you do biogas, if you do other technologies, obviously it's different. But this is an unused resource. But first, we should not generate, right? Because we need land, water, fertilizers to grow this biomass. If we really have this as waste, right, we should find a way to reuse it. Yeah.
Maybe one more question? Yeah, go for it.
I had 2 questions, but my first one was more so we're in a decentralized system. Like, how can we is it possible to use like food scraps to create our biomass? Is that
Yeah. Yeah, so we use it very widely. So this is waste treatment. So as I mentioned, waste biomass is from manure, many sources, right? Can be manure, can be food residues, crop residues, can be food waste, organic food waste, can be wastewater. So you can use this with anaerobic digestion So here you have waste biomass, whatever waste biomass, organic, obviously, right? That can be decomposed by microbes. Anaerobic digestion, you have the microbes that digest the biomass. And basically they have a strain that they don't show here, that is digested, that is the nitrogen. That is the compost, basically. Okay. And then you have the gas part that is called biogas. Biogas is half CO2, half methane. CO2 you usually make it, but you can do carbon capture. The methane you can use instead of fossil natural gas, is renewable natural gas, and you can use it for everything. This light bulb probably is running on natural gas, right? So you can use it in our energy systems. Yeah.
And my second question was, you said a country like Uganda,
Yeah.
they have
Very high price. Yeah.
yeah, it's expensive for them to import fertilizer. So in a country like that, there's food like they not use fertilizer.
They don't use fertilizers. So this is to answer also this question, right? Which Kyle is working a lot, Kyle and his group. Where is it? Here. So here you have nitrogen demand, fertilizers. In blue is where you have agricultural intensification. In yellow, you still have agriculture, but you don't have intensification, so you don't have irrigation, and you don't have fertilizers because they don't have the technology, it's too expensive. Here they don't apply fertilizer because it's too expensive. And obviously they don't have the facility to produce them. Right? There is only one year in Nigeria, which is mainly for export, by the way. So this explanation, yeah. So if you do this decentralized approach, you can close the ingot, so you can produce more food locally, but obviously, you need the capital expenditure. These are millions of dollars, right? And so you need someone going there and giving the millions of dollars to produce this facility. And when it's large scale, it's billions of dollars. When it's small scale, like this facilities that we Haber-Bosch 2.0 is tens of millions of dollars. So it's another order of money to maybe you find the capital to build it, right? And manage it. Yeah. But still a lot of money, right? Very expensive.
All right, let's thank Dr. Rosa.
Thank you.
You everybody have a nice rest of the day.
Yeah. Stop recording. Ci vediamo le 4
Vedi che sono